All right, I think we can start. Welcome everyone to this week Autonomy Talks. This week is a pleasure to have Professor Cody Fleming, who is an associate professor in mechanical engineering at Iowa State University. Something about him, so he received a PhD in aeronautics and astronautics from MIT, and before joining Iowa State, he was actually a faculty at the University of Virginia. And we had a talk from his PhD student, Georgios Bakirtsis, a couple of months ago. Dr. Fleming is interested in developing theories and methods to assure safety and security of control systems and autonomy. The applications he's interested in to include aviation, air traffic management, urban air mobility, and automotive. Today, this talk is titled Physics and Learning in Prediction and Control, and we are all very excited to hear what he's going to tell us. So go ahead, Cody, the stage is yours.
All right, thank you very much. So I'm gonna, for most of the talk, I'm going to talk about and describe some of our work mostly in planning and control. And if we have a little bit of time, I'm gonna get a little bit into some work on multi-agent prediction. And I know that Emilio's group has some recent results there too. So that could be interesting. I'm happy to take questions whenever. So if you want to stop me in the middle, I'm happy to take questions and I can speed up or slow down as necessary. So, and of course, in the area of COVID, let me know if there's any issues with sound or anything like that. So as GOL mentioned, this is Yorgos Bakirtsis, who was one of my PhD students. He successfully defended about a little over a month ago. So congratulations to him. And you all know him also from helping out, I think, with the ACT 4E class that you're putting on. And thank you for putting that on. It's been excellent to follow. So he's been doing a lot of work with compositional theories and category theory and CPS. I'm not really going to talk about that work except to just promote it again. And you can go back and look at his YouTube talk from January. And also to note that he just finished and he's took a postdoc at UT Austin with Ufuk Toku. So congratulations to him on that. So moving on, just a few observations. So I'm talking about physics and learning in planning and control. It's interesting now, having gone to several conferences and submitted papers in both conference and journal venues in the more traditional controls field. And there's this interesting observations about what we see when we talk about learning. One thing is, if you go to, for example, CDC or ACC, any of the sessions that have, the notion of learning in them are packed with people, right? And they're usually in the biggest room and they're still, spill out. And so there'll be hundreds of people in these sessions. And yet the traditional controls people will say that they already have the answers. And in fact, you'll hear that sometimes. And you'll see that in some of the reviews you get if you submit a paper. Which is kind of interesting. So it's made me kind of pause and sit back and think about what's actually going on here when you're doing learning in the context of controls. And there's actually some good papers on this. There's a tutorial paper from, I think, CDC 19 from Nikolai Matney and others that actually gets into some of the similarities and differences. For example, between reinforcement learning and control. So I'm not going to get into that too much. I'm going to talk about it briefly because it's informed my thinking. So controls people look at a system like this and typically try to describe the plant with, let's see if I can get my laser pointer, with difference equations or ODEs, and then design estimators and controllers to get the dynamics they want. And so things like stability, controllability, observability, performance. So all the usual things, including robustness and system identification. So these last two are particularly close to what you might see in reinforcement learning. But the controls people typically want guarantees, and there's an increasing number of people in the learning community who also want guarantees, but oftentimes the guarantees that they're looking for are a little bit different. And then of course, if you go into more of the pure machine learning conferences, a lot of times it's just this machine learning trick worked, and congratulations, it works better than the state of the art, which is a little bit dissatisfying. So this is the controls view of the world, and here's a brief picture from Sutton and Bardo's work on or book on reinforcement learning, where we have an agent that interacts with the environment, takes actions, observes what happens with respect to those actions, receives some award, and updates policies, right? And so at sort of a 30,000-foot view, you could see that this is maybe somewhat similar to both system identification and maybe stochastic control or stochastic optimal control. A second thing that's really interesting for me, and this has been where I've really started to think about, what we're doing when we model things, is using reinforcement learning in the context of planning, right? And so we're explicitly trying to learn a model, use that model for planning and updating our policies accordingly, right? So this is a little bit different than the traditional reinforcement learning loop. But I've been thinking about this. Is this even an appropriate paradigm? And it's mentioned that my interests are in aviation and air traffic management, as well as automotive, which I think is the automotive domain in particular for Emilio and a bunch of people in your group. Is this an appropriate paradigm to just use this notion of acting and exploration to learn what your policy should be? Right? I don't want you to do that in your car, right? It's just to start experimenting and figuring out what works if I'm going to be riding my bike next to your car, right? So this has led my thinking in terms of, when can we use physics, or when can we use first principles, and write down formal models, essentially formal predictive models of what's going to happen to the dynamics of our system or the dynamics of the environment, right? And when to use versus when to use purely learned models, right? And is this an either or thing, right? And so I think for me, I've really been thinking about, well, can we and should we use both, right? And if so, how should we do that? And so a particular example that I've been thinking about in a particular way actually involves transportation. And so this is, hopefully this video is showing. Right, so this is, I'm not going to show the whole video, but we've all been at traffic, and right, so when we drive in a very complex traffic scenario, we use a lot of heuristics, we use a lot of experience, and we don't necessarily have a formal model in our brains to be able to plan and act accordingly. But there's a lot of interesting problems from the perspective of autonomy, right? And so one approach is to have more centralized control over everything. So you have communication devices in every car, and you might have a centralized planner. There's a lot of interesting work in terms of intersection control that does that, including from my group. Having better prediction, right? If we have better predictive capabilities, we can get better throughput. And then using communication, right? So I don't necessarily have to rely on my own prediction to do better planning and control. If you or your car, right, if your car is doing its own planning and it can just communicate what that planning is to me, I can do better planning myself and better control myself, and that there can be either sort of top-down centralized coordination, or that there could be more of like a distributed consensus type of coordination. But either way, this notion of communication between the cars could help improve the congestion in that brief video that I showed. So, so we started looking at connected vehicles as a solution here, and connected vehicles themselves have a million open questions, right? So if you want to get in an interesting research area, in addition to autonomous cars, is getting into what happens when the cars communicate with each other, and how we use that for the autonomy that's on board. So I'm going to skip this video. But one of the things that we've been looking at is the fact that, and I hope this doesn't happen during my talk, but that communications are not very reliable, right? And so we've all had the situation where we are, I can't hear you, or I can't get my text to go through at a busy event or something like that. And that's fine when we're, talking on our phones. It might be fine if I would be disappointed, of course, if my Wi-Fi went out right now. I couldn't give this talk, but it wouldn't necessarily be safety critical, right? So packet losses and loss of communication in this context, if we're relying on communication for our autonomy, is very, very not good, right? So, and there's strangeness in wireless communication. So here's an example of an experiment where there are two cars following each other, and they follow each other under an overpass. So right, they go underneath basically a bridge. There's a bridge that goes over top, and there's multi-path interference, and they have these packet losses, right? And so there are issues with communication that go beyond just the communication stack, right? So the various layers in the communication stack have their own issues, but just the fact that you're communicating out in the physical world, and there's all these things going on with line of sight interference, with multipath interference. So we have to be able to handle those things. And I'm not going to talk about this the communication side very much today, other than that this was a motivation for me thinking about this notion of physics and learning in the context of control. So what if we could actually predict wireless performance into the future based on states of the physical world? And so myself and some colleagues actually looked at doing this. And like I said, I'm not going to talk about this in detail. But this is basically a big machine learning problem. The physics aren't understood well enough, and they're so high dimensional that at least at this point, you can't write down a scalable, set of differential equations to predict packet delivery rate, for example, or packet loss rate. And so we developed a very a relatively complex set of recurrent neural networks that could predict wireless channel communication into the future, and we get pretty good results. But this is not something that you can typically deal with from a control theoretic paradigm, because this thing right here is basically a black box, right? This is a very high dimensional, highly nonlinear thing. Okay, so this led us to this notion of data-driven MPC, data-driven model predictive control. And the hypothesis here was that we could do better if we split what we quote unquote knew with from what we did not know. In the sense of we might have a good description of the dynamics of our vehicle and maybe some other parts of the environment, but we don't necessarily know what's going on with this deep learning based predictor of wireless, right? But we want to make sure that we have a good wireless channel and that we can update our policies depending on what that wireless channel is doing, right? So that was all the motivation to get to our version of data-driven model predictive control. Let me take a drink here. So the basic notion of this predictive controller is loosely based on some of Borelli's work and Ugo Rosalia, I believe, on iterative. So their work was in the context of iterative learning control and repetitive tasks. We don't necessarily have a repetitive task, right? So we're just trying to drive through a busy intersection for the first time. We don't necessarily get to do it, 100 times in a row. But either way, the basic notion is this. So here's an example of the closest credible flight I could find between myself and Zurich. So this is Chicago O'Hare flying to Zurich. And let's say that I tried to find my way to Zurich. And let's say that my first flight, for whatever reason, I started flying south and then ended up turning back north and found my way to Zurich. That I can actually use this first trajectory and iterate on it and essentially guarantee that every iteration will be better than the last. So here's basically how it works, right? And I'll eventually converge to this optimal, great arc from between Chicago and Zurich. And so our algorithm is basically trying to do this in real time, right? I'm trying to get from, I have a control objective and I'm trying to achieve it. And at each iteration of my algorithm, it'll get better than the last one until it converges. Okay, so just really quickly to review a little bit about model predictive control. So I won't belabor this point and assume at least a little bit of basic knowledge about this. Right, so we have this objective function that's or a cost function that's a function of our states and inputs. So this is H here, subject to our dynamics. So in the context of driving, this would be, maybe like a 3 degree of freedom bicycle model or something more complex. Or if it's an aircraft, it's a 6 degree of freedom attitude model or something like that. Right, and then we have a starting point. We might have a goal condition or a terminal cost out here. And then constraints on, right? So this could be stay out zones X and constraints on our control inputs. Okay, and what model predictive control is, it solves this for a sequence of inputs U, and typically what it does is it applies the first one and then starts over again at the next time step. All right, so that's model predictive control 101. What we're doing is adapting this problem. So what if we have a situation here where this should look like the same problem, but now we have this additional thing here. So what if we have, so this Z hat is basically a black box, right? So usually we can write down H, and H might be quadratic in X and U, but Z hat is just some unknown function of X and U, right? So that's a black box that could come from a deep learning type of model. Furthermore, we could have something down here that's also a black box. So anything with a hat here, so here we have another black box, and this could be subject to constraints, right? And one of the challenges, in particular with this communication, wireless communication, is that we have this coupling between our dynamics, right? So our evolution of X and U, and our and the output of our black box, right? This is also a function of X and U, but it's also a function of possibly a bunch of exogenous variables as well, right? So in the context of communication, this is things in the physical layer of the communication stack, or something in the protocol, or something that you can't necessarily observe. So now we have this thing where, okay, so we have unknown functions all over the place, in addition to our usual optimal control formulation. And so we've developed techniques that basically can handle this, and they can handle this quickly and optimally. And so that's what we'll explore next year. So some basic definitions to get to that were used in our papers to get to where we needed to go, which is this notion of if I'm trying to get to a set of states S, the one-step controllable set K1, right, is the set of all states that I can get to S from in one step, given my constraints on my control input and my dynamics. Right, and you can extend this backwards. This is sort of a backwards reachability concept, all the way back to n steps. And then you can keep going all the way out to infinity, right? And so these pictures are just notional. These look like very weird, kind of higher dimensional manifoldy looking things. And you can also do this for, if you're, instead of getting to S, you're getting to a, you're trying to get to a control invariant space, then you can have an n-step or maximal stabilizable set. And so we use this notion, and again, this is similar to what Borelli was doing with their LMPC work, but we've actually changed it significantly to do something in real time in a non-repetitive task. And so we use this notion of a sampled safe set. So instead of trying to compute the backwards reachable set, which is challenging to do, we actually use our experience, or in this case, we use every time we cast a trajectory forward, if it successfully reaches our final state, we keep track of those. Right, so we might keep track of this particular trajectory and use it as a success case to learn from. And so this sampled safe set is the intersection of any successful trajectory at the previous iteration. So this J-1 right here is a successful, so star and J-1 are a successful iteration at iteration J-1, the previous one. And the sampled safe set at iteration J is the intersection of all these trajectories with the n-step controllable set from my current state, right? And I'll show you graphically, or at least pictorially, what this looks like. So this is basically what I said here in words. And so basically what this looks like is, okay, so I'm going to use this, so I have this previous trajectory that was successful, whatever our success metric is, which is sort of application dependent. And now I'm trying to find a new trajectory that's better, right? Until I converge on an optimal trajectory. And so I'm currently constructing this trajectory at iteration J. And at time t, I'm basically going to pick, I'm going to try to find any n-step reachable states that are in the previous trajectory, J-1. And that's basically what this algorithm does. And it keeps doing this sort of in an MPC type fashion until it converges. And it's kind of amazing that this works. And it works, and it has some interesting provable theoretical properties. And again, with this mix of, it can do this with an arbitrary black box subject to a few certain assumptions. So this is another representation. We'll skip these. So properties, we can show that if the algorithm is feasible, so if we basically have a feasible set of inputs and states at time t equals 0, then at every iteration, we can prove that the algorithm will be feasible at time t plus 1, right? And so you can keep doing this out to infinity, right? So basically this will be so the key is finding basically a feasible first set of inputs. And once you do that, it's forward invariant. The second thing is that every sort of complete trajectory, so this is sort of the inner loop thing here. Every complete trajectory J for this infinite time problem is better than the last one, right? So this is guaranteed to converge to at least a locally optimal trajectory. All right, so I'll show this on a toy problem, a fairly realistic toy problem first, and then I'll show this actually working in action. So here's a context of this is an agent with basically bicycle dynamics. So think of like a simplified version of a car. So it's nonlinear dynamics, and it's trying to get from this starting state XS on the left. So it's trying to get from here to here. And even though we can see these contours, the controller can't, right? So the controller just sees, I have this goal that I'm trying to get to, and I'm going to get, every time I iterate, I'm going to get feedback from this black box that tells me, okay, right, so if I'm right here, that's a really bad cost, versus if I'm out here, that's a really low cost, right? So the controller knows its own dynamics, but it doesn't really know what this underlying function is at all. Okay, and basically here's how it works. So it has this first guess in yellow, which is kind of all over the place, and you can tell that's probably not a very optimal thing to do. And then it's going to use these n, and I think the length of n here is 10, and it's going to keep trying to finding sequences of small sub-trajectories that basically follow this algorithm, right? So that the n-step reachable set is intersects with some previous state in the previous iteration in yellow until it gets to the end, and then it'll do that again. So here's what it looks like. So here's the first, right? So that happened fast. I'll slow that down. But it basically converges in 4 or 5 outer loop iterations, and so we can run that again. And it's basically done here. So here's, my computer's frozen. Uh-oh. Oh, what's happening? Okay, so here's essentially a little bit of a slice of what it's doing, right? So it's got this 10-step iteration on top of this outer loop trajectory, and it's basically incrementing one time step at a time, and finding n-step reachable trajectories that are within the previous outer loop yellow trajectory, and it does that basically until it converges, and then it basically picks the best combination of feasible sequences of trajectories to find the next long outer loop trajectory like this. And then it starts over at the beginning, does the same thing over, and does that till convergence. Right, and so here's the optimal trajectory, and this is actually a globally optimal trajectory from S to F. All right, so that was a toy problem. Now let's get back to our case study. So here's the case study that we're doing is basically 2 cars where there's a leader and a follower, and they're trying to optimize, fuel and state costs. So they're trying to get to their destination fast, but they're also trying to maintain connectivity, right? So here's an example of cars driving under a bridge overpass where there could be interference and things like this. And we have a data-driven cost to go. So our cost is essentially a function of not only our controls and our states, but also this communication. And this comes from a purely black box, this big LSTM. So it's a recurrent neural network that's pretty high dimensional. And basically what happens is every time that the DMPC casts a candidate trajectory, it passes that to this LSTM over here, gets an update on its data-driven cost to go right here, and it just goes back and forth basically until it finds an optimal balance of communication quality and state and control costs. So here's what it looks like in action. This is two F1 1/10 scale vehicles. If you're familiar with the F1/10 project, the lead car is actually driven by a human, and then the following car is basically doing pure pursuit. So its goal is to basically follow the car in front of it while also maintaining communication, which might involve actually slowing down, right? So I might want to increase my distance to reduce multipath interference. So here's an example of it running. So it works fairly well. Actually, the problem with that experiment is that it's actually hard to get communication and to degrade in such a benign environment. So what we do is actually attenuate the communication signals to sort of force it to do that. Okay, so some results about DMPC. So the number of DMPC iterations, this is the outer loop is L, and the time horizon is N. So that's this inner loop thing that's trying to basically search for n-step reachable sets that are within the previous DMPC iteration. Our time complexity is unfortunately 2 to the ln. But the good news is that these numbers are, especially n is controllable. So that's sort of a hyperparameter that we select. So in practice, this actually works pretty well, and it works with even nonlinear physics models. So this essentially creates basically an integer program. So a mixed integer program, and can solve it arbitrarily. So what it achieves is, what's interesting to me is that I can actually use data from a deep neural network, right? So we can't really model wireless communication in a short form, sort of closed form way. And so DMPC actually allows us to sort of sample data from this deep neural network in shorter and more frequent time steps, and essentially adapt our strategy very quickly in doing that. So we get more coverage of the space in a shorter time, and therefore converge to optimal solution faster. So more generally, I want to talk about sort of architectural considerations as we move away from this particular wireless communication application. So this is a picture, again, adapted from Sutton and Bardo, which is reinforcement, the famous reinforcement learning book. And this is, using real experience from the environment to update our policy, our control policies, and also using learning to develop models, right? And so I think, one thing as I go forward in my work, but as we go forward in the community, especially in safety critical applications, is what is our expectation, not only of these policies up here, but also about these models, right? Is it okay to just have this black box? Fortunately, there's some really good work out there, and in particular from people coming from the formal methods or even the controls communities actually looking at verification of black boxes. So that's good. That's a good contribution. But another thing is, why not just combine things we already know? You know, do we really need to use a deep neural network to learn a 6 degree of freedom aircraft attitude model, right? We already have really good parameterized models of those things. So let's just use those and maybe combine them with learning. And so in our particular case, and then the second thing is, you know, reinforcement learning or the learning literature they look at asymptotic guarantees, right? So I want to have an optimal policy if I have infinite experience and infinite time to learn. We want to speed that up, and that's not necessarily a good kind of guarantee that we want. As far as architecture for our work, this is kind of what we're doing, right? So we have physics over here. So this is physics, and then we have black boxes coming in here and here, and we're able to split those out and actually get guarantees on convergence that's faster. But also we can at least have mathematical guarantees that will adhere to our state constraints, which are our big safety constraints, right? So, so again, the big takeaway here for me has been, you know, when we're talking about models of things, what kind of models are we talking about? And I have sort of feet in both worlds. I have feet in the machine learning world, but also the more traditional. I'm in mechanical engineering, right? That's my appointment, where we have more traditional models of things. So our work here has really been trying to get at this idea that it's not either or, and it's not the controls community already has the answer, and it's not that AI or deep learning is going to solve everything. It's that, what if we combine the two, right? And can we get synergy out of combining the two? So, so that's basically the first half of my talk. Well, it's the first probably 80% of the talk. But I'm going to switch gears now very briefly. So that was about planning and control. And I want to talk very briefly, especially to this group, about prediction. And so we've been doing some work in navigating in shared environments, right? Which is what you have to do when, this is a picture of Grand Central Station in New York. I know that, right, in Zurich, you've got similar problems when you're going to take the train. And it's interesting just to pay attention when you're walking through a busy area or like an airport, how you actually sort of keep track of what everyone is doing. And so we've been working on this particular problem with dealing with pedestrians, but we've also been looking at this in terms of automotive, and even interestingly, I don't have a naval background, but looking at this is predicting ships, right? So ships or boats or paddleboarders or surfers or whatever, predicting their motion in busy ports or harbors. So the hypothesis here, and this actually goes with this notion of just using simple physical observation. So it's, if you squint hard enough, this is related to physics and learning, is that we can actually do very good prediction of pedestrian motion or whatever agent. It doesn't even have to be pedestrian, just by looking at their orientation, right? So that's the only physical observation we really need to get state-of-the-art prediction. And so the problem basically looks like this, where if we have basically n pedestrians, so if there are, you know, 15 pedestrians that are walking around and I'm an agent, either pedestrian, cyclist, car, and I'm trying to navigate through there, if I basically have a sequence of observations, I can create a sequence of predictions into the future. So that's what this problem statement is basically saying. Using sequence modeling approaches like long short-term memory networks or recurrent neural networks makes sense. And there's a lot of work out there, including from some of your colleagues at Stanford who are doing work in this area. However, using just vanilla LSTMs cannot predict behavior for collision avoidance, or they can't do it well enough. And so what we're doing in this work, and I'll try to wrap this up briefly, is essentially if I have the orientation of a pedestrian, so if I know it's bearing, right? So if GOL is walking and he's right in front of me, but he's walking in the same direction, that's different if he's walking right in front of me and facing me, right? So that's very intuitive, right? If someone's walking right at you, you react differently than if someone's walking away from you, right? And if you're walking sort of from my left, but you're facing right, then that's going to be different if you're walking from my left and facing left, right? So this is obvious, right? It's almost trivial, but we're actually able to encode this in a learning framework. And we use this notion of domain, and the name domain actually comes from the shipping and maritime, I was going to say domain, application area. And we're actually going to learn this domain, which is the area around a pedestrian beyond which the trajectory of another pedestrian does not influence the trajectory of this pedestrian, right? And this is actually sort of a manifold, right? Because it's a combination of both bearing and heading, right? So it's 360 degrees sort of twice. And we're able to learn this basically in terms of a very simple algorithm, right? So we basically learn this S right here is the domain. And it's think of it as a lookup table. Basically, it's a matrix that's a combination of heading and bearing. I look that up, that gives me a number. I subtract the distance between the two agents, and I take a ReLU, right? So it looks like this, right? So if that distance is sufficiently far away, there's no influence, right? So it's basically sort of a higher dimensional encoding of distance, bearing, and heading. And we're able to actually learn what this shape looks like. So this is a learnable parameter. And let me skip this one. So this is an example of pedestrians, and I realize this is a lot to take in. What this is basically saying is, okay, so if the relative heading is 315 to 345, that basically means you're kind of facing me like this, right? So you're facing me at negative 30 degrees, where 0 basically means we're heading in the, 0 means you're facing right towards me, right? So negative 30 means you're clocked this way. Basically, you're facing this way. Right, and we're able to learn that, of course, you're more influential if you're up over here, and you're less influential, of course, if you're down here. Right, so it's very simple conceptually, but it's interesting that we can teach a machine to learn this, right? So if negative 15 to 15 basically means you're facing me, right? So you're more influential if you're right in front of me. And of course, if you're at minus 180, you're actually facing this way, right? Which means you're less influential than if you're facing towards me. Okay? And we're able to do that for all possible combinations of bearings and headings. And we encode this in a large, I'm not going to go into all these details in the interest of time, but basically, so down here, we're able to achieve basically state-of-the-art predictive capability. And here's Trajectron++, which came out of Stanford, which is also very powerful. We're actually able to do essentially just as well, but with slightly faster inference time, because the models are a lot less complex. The next thing we're trying to do now is actually do multimodal prediction. So instead of just saying, here's exactly what you're going to do, here are the possibilities of what you could do in the future so that we can do better planning in, right? So we can have contingency plans. I could go left or right, depending on what maybe my next two observations are. So with that, I'll wrap it up. And just to conclude, so we're developing, predictive controllers and decision-making with unknown functions, e.g. from deep learning, that operate interdependently with functions that are explicitly modeled. we're trying to do that in an efficient way at real time. Other work, of course, we're looking at interactions between humans and autonomy, not just in pedestrian prediction, but also in, for example, urban air mobility if we have someone on board an autonomous aircraft. And then, of course, you all know there's other work we're doing, but you know of Yorgos' work on co-design for safety, security, and other properties of CPS. So with that, I will wrap it up and open it up for questions.
Thank you, Cody, for the great talk. Are there any questions from the audience?
Yeah, thanks, Cody. Interesting work. A lot of stuff to talk about. Now, one of the things about prediction is, first of all, is how would you, I'm not sure I got, how you represented and how you acted on uncertainty in the prediction, and also how, and to what extent you model the effect that your decisions or your behavior has on the things that you're predicting.
Yeah, that's so both the uncertainty actually, so the first version of our work was actually looking at sort of just, and this is a problem I think with the machine learning community, is just how accurate is your prediction, right? So you have a loss function and it's how accurate is my prediction over a time scale, so over the next 5 seconds, or, and there are different metrics for it, which are standard kind of in the machine learning. But the problem is, like you said, is what if I'm wrong? And so here what we're trying to do is actually have a little bit of quantification on uncertainty, both in 2 different ways. One is that I could have predicted that you would turn right, but you turned right by 10 degrees instead of 11 degrees. But the second is I predicted you turned right and you turned left, which is totally different, right? Because I might have also gone that direction. And so we're trying to do that with a notion of GANs, or generative adversarial networks. But again, this isn't very theoretical. So I think some of your work is looking at game theory, and you actually have a better theoretical handle on what's happening. So that's promising. What was the second? Oh, the second question I think is deeper and more challenging, which is that all the agents are mutually interacting, right? So if I start going like this, you're going to start going like this, right? And we have that happen when we walk through busy areas, right? You both end up going the same direction for a while, and it's actually a very game theoretic approach. So one thing that we're trying to do here is, so this our scan model actually models all these interactions. So if I go left, I can actually predict what you will do. But now what we're trying to do is sort of combine the first half of the talk, which was the predictive control that can deal with black box variables, with this work in a game theoretic way, right? So if I go straight, I can use this model to predict what everyone will do. If I go right, here's what everyone will do, and I'll go left, and then I can pick an optimal solution. And so we're kind of in the middle of that work right now.
Thank you. Any thoughts on like a multi-model? So what if you had? So we're like saying like quantifying uncertainty and things like that, right? But the difficulty is when you were saying, I don't really care if you turn right by 10 or 11 degrees.
Right.
That doesn't really matter that much, right? But I do care about whether you will turn left or right? So then, in a sense, I care about what the distribution of what your potential behaviors looks like, and especially in cases where you have very definite multimodal distribution, right? So kind of detect what are the major options that the other person has, right? And to what extent I can influence, what they will do, and things like that, right? So I just wonder, how you can incorporate this like a multimodality in the learning kind of approach.
So we have one idea that is using our notion of right. So this scan, where is this? So scan. I didn't talk about the architecture very much, but SCAN stands for socially context aware networks. But this notion of domain, and this is a higher dimensional thing than what I'm showing here, but the idea is to actually encode the learning with a notion of a distributional notion, where it can learn basically a distribution across actions that respect the domain, right? So if we're facing each other and we both go right, that means we miss each other, right? If we both go left, we also miss each other, right? So those would both respect the domain, but they would be different slices of this manifold. And if I go straight, that means you're going to have to make a hard left or a hard right. And so there's a distributional notion across basically multiple trajectories that respect essentially different slices of this domain manifold. And so that's one idea. That's sort of how we are proposing to do, where is it? This essentially right here. But the problem is the reason we need sort of these compact representations that this is just two agents, but now I have a car driving through an intersection and there's 100 pedestrians walking across, right? So we need something that scales, which is, again, a reason to use learning is that it scales. A reason not to learn it is because it's very hard to reason about. So we're trying to sort of hit that balance. But yeah, very good question. It's challenging, but that's kind of where we're at currently with it.
Yeah, thank you, Cody. I don't know if somebody else has any other questions.
Yeah, Nathan, I think Nathan McMahon has a question. You can go ahead.
Yeah, so I'm not from the field, so it's quite possible you've answered this in the talk. And I just didn't see that this is the answer to the question. But you were talking about difficulties in wanting to provide guarantees and not doing that so much from a machine learning side, but you want that from a control theory side. Have you considered the kind of formal guarantees that you can give from machine learning? I'm imagining something like on agnostic pack learning, but probably something more sophisticated for your problem.
I'm writing that one down. That's a good one. So there's a general. So have I considered notions of guarantees from the machine learning community? That's sort of the general question, right? And then specifically from, so there, and I was being very hand wavy with the types of guarantees. So, I mean, if I were to be critical of the machine learning community, is that probably 95% of it doesn't even care about guarantees at all. I don't know, 95%.
Yeah, I'm thinking very much from the mathematical machine learning as opposed to the general machine learning.
Right. And so that 5% or whatever that number is, I think does have some interesting results. I think in the reinforcement learning community in particular, the types of guarantees they're looking for tend to be different. The traditional reinforcement learning people, so they're looking for asymptotic guarantees and so convergence guarantees that are a little bit different than what we often need in safety critical domains. But this is a good question to look more at the and you know, Manfred Murari and George Pappas and others are looking at sort of bounded input, bounded output kinds of guarantees with deep neural nets, which I think is a promising start. It doesn't really scale yet, but I think that's a good start. And I'll take your suggestion as well. I haven't looked into that, but that's a good one.
Yeah, I guess my thoughts were for binary classification, this is all I know. So that's why it's this simple. For binary classification offline, this agnostic pack learning can say, if you take so many samples, you can guarantee that you're within epsilon of the best case scenario, 1 minus delta out of the time. So that's why I was thinking it sounded useful here. Sometimes you're going to have an issue, but as long as that delta becomes less than the chance that a human's going to have an issue.
Right. Yeah, that's good. If you don't mind, could you send me an email? You can find my email on this website.
Yeah.
Okay. Yeah, that's great.
All right. Are there any other questions? I actually have one more, maybe eye level, which is you said in the beginning of the talk you're following these compositionality classes and you're interested in the topic. If you look at this talk, where do you see these compositionality approaches making a huge difference in the future?
Well, so I think obviously it's fairly straightforward. I mean, our group, as well as your group, already has probably the equipment to do any of the stuff with controls, right? And things with sort of architecting and co-design. I think a big question for me is, I put up this kind of crazy looking diagram, but I'll try to answer this quickly just in the interest of time. But so this is kind of like pseudocode. This is like a information flow, but you could also think about this as an architecture, right? So we think about where do we put, typical kind of embedded systems types of applications? Where do we put black boxes, deep learning types of things? So that's an architecture question, which I think is related to a lot of your work. What I think is needed is more categorical treatment of the various machine learning methods, which is something that we're interested in. I think Yorgos and I are going to be working on. Of course, he's leaving me, but I'll follow what he's doing, and maybe I'll be lucky to hire another good student that's as good as he is. But this is a problem with finding good students, then they leave. But I think the main thing is to sort of even take some of the work that you've been doing on co-design and think about some of those components. If they looked like this, right? They're a deep neural network. What kind of categorical flavor of stuff would we need? And I don't think we're quite up to speed on that as relative to the other types of components that we usually deal with, right? So, and maybe some of the work will come out of the formal methods and mathematical community, like Nathan said. So I think there's potential for sure.
Great. By the way, I think Spivak started working on learning recently and just gave a talk about it. So maybe. Unfortunately,
he'll beat us all to it. But, yeah. So I think and Aaron Ames as well.
Yeah.
So it's very good.
There is somebody in the chat mentioning that maybe you want to copy paste that comment for you. I don't know, that your work reminds him of information flow studies.
Where is? I can't find the chat.
Yeah, it's somebody. I can really read it. It says, Cody, your work reminds me of information flow studies for insect ants during tandem runs. Leader follower. You may want to check out the work of Gabriele Valentin at Arizona State University. Okay. I took a screenshot and I will send it to you.
Okay, thanks. For some reason, I have like multiple screens open, so I can't find it. But, okay, thank you. I appreciate it.
Great. So any final question? If not, I think you noted down the website of Cody's lab. You're free to reach out to him for deeper questions. Thank you very much, Cody, for the great talk. I wish you all the best for this new adventure at Iowa State, and hopefully we'll meet each other live at some point.
Yes, definitely. I think it's opening up, so I hope that happens soon. So,
Great.
all right. Thanks,
Thank you very
everyone.
much.
Thank you so much for having me, and we'll see you soon.
See you soon. Bye-bye. And thank you all for participating.
you.
See you all next week.